our first talk, we're going to have Inbal Levi. And Inbal is an embedded software engineer with a passion for high performance. She is a director at the ISO C++ Foundation, co-chair of Library Evolution, chair of SG9 Ranges Group of the C++ Standards Committee, and of the ISO C++ NB, and one of the organizers of CoreCpp Conference and User Group. She is going to be presenting a talk on customization methods, connecting user and library code. Please give it up for her.
Thank you. So thank you for the great opening. That was amazing. I would like you to come and open our conference. You're an amazing host. So I hope you can all hear me well and see the slides. And if so, I'll start. So thank you again for inviting me. It's great to be here. So as you've correctly asked, what are customization points? This is the target of my talk, is to be able to explain that and make everyone feel more comfortable with those terms, which are quite technical, but also I think very useful. So let's start. So as you've mentioned, I'm a C++ developer. I work at SolarEdge, which is a nice company doing solar systems. I'm an active member of ISO C++ work group. This is the work group that works on the standard of C++. But you already mentioned that we can jump forward. I love software design, and I also have a passion for cataloging, which is the main reason I'm giving this talk. So this is our outline. We're going to start with understanding what are customization points really. Then we're going to move to an overview of the existing methods from a broad perspective. We're going to compare different customization point methods, and then we're going to talk a bit about what next for C++. Both the first parts will contain some useful history to understand how those things were developed. So let's start. What are customization points? So you already are familiar with customization points. You're probably already using them in your everyday code. And I'm sure you've seen this example before. So let me just go over this very briefly. This is customizing the stream output operator. So let's say I have two different developers on two different sides of the world, just like we speak right now. I speak from Israel. And one of them Alice have written this library side. And this is a logger. And Alice have written the logger to do all sorts of things. But she also needs to understand how to print this type that comes from Bob, that is actually the user of this library. So Bob would need to customize the printing of his own type. So we can see here the user type, and here we can see the library logger. So generally, throughout the talk, I'm going to use the same way of presenting things. We're going to have the library code on the left and the user code on the right. So now Alice have written her library, and Bob have written his way to print the user data. And we can call the library code with the user type and get what we expect. So basically, what Bob have done here is customizing the customization point of the library. So I hope now it sounds less scary, and we can move on to what are the possible ways to do that in C++. So first of all, I still want to focus on what do we look for in such mechanisms. So a library from Wikipedia. A library is a collection of non-volatile resources used by computer programs, often for software development. But I think this term neglects the human factor, because a library is often shared between different developers, possibly from different parts of the world. And customization points add this ability to communicate and integrate the library and user code, which is as you can probably understand, not very trivial. So yeah, let's see how that works. So the term customization points were first mentioned by Eric Nibbler in a blog post from 2014. And you have a link here, so you're most welcome to go and find more details. In 2015, it appeared in an Workgroup 21 paper. So the standardization of C++ works with papers that are being published and then accepted into the standard. And this was one of them. And there, Eric Nibbler, which is, by the way, also the author of Ranges, have suggested this term. Customization point, as will be discussed in this document, ergo with the paper, is a function used by the standard library that can be overloaded on user-defined types in the user namespace, and that is found by argument-dependent lookup. So argument-dependent lookup, we're going to see in a few seconds what that is. But in general, we're going to expand Eric's term in this talk to something more general. So for our talk, a customization point is an integration method exposed by the library that can be used by a user to customize or hook the library according to their needs. So we will be going over Eric's customization points, but we're going to refer to them as the original customization points. So notice this minor difference. So we've now reached to our first conclusion. Customization points are means of integration of library and user code. So an additional thing that we need from customization points, users need to understand which ones exist. They need to be able to opt in, add implementation based on their own understanding, and need to avoid accidentally running over library implementation. So for example, if Bob would have written a type that creates its own logger and do the whole login thing by itself, then it couldn't be integrated with the library logger that we saw in the example before. And Barry Rasvin talked about both this and the previous aspects in his very good paper. We need the language mechanism for customization points, which I will highly recommend all of you to go and read. It's a really interesting, I think, paper that analyzes very similar to what I do here in the talk. So I'll let her show you links with all the relevant things. So we now reach our second conclusion. Customization points are means of communication between library authors and library users. So to bring up additional aspect, customization points determines which entities are shared between the library and the user, and that could be functionality. It could also be terminology, data, and we'll see soon what I mean by that. And we'll focus on aspect of user using library types, but it's not necessarily the only case. Libraries can also use other libraries. So yeah. So to reach our third conclusion, customization points are means to embed specification from the user into the library. So to summarize, they're mean for integration. They're also means of communication. So we need to be able to signal what we want to customize with those customization points, and the user needs to be able to understand that and customize on their side. And customization points are means to embed specification. That would be the user being able to tell the library what the desired behavior. So I'm going to stop now and ask if there's any questions so far to this topic. And if there are, I can see there's some things in the chat. Okay, no questions. Great. So let's move on. So for the purpose of this talk, we still need to be familiar with some terms, and I'm going to very briefly go over them. I've already mentioned one of them, which is ADL, argument-dependent lookup. So basically, to compile a function call, compiler creates a list of candidate functions, and then find the correct overload. So this process of understanding which is the correct overload is a process called overload resolution. Function candidates picked according to function names that would be called name lookup, and they may include template argument deduction. So if we have templates, we'll be able to create some candidates from them. And argument dependent lookup, which means that if we have types that the function accepts, we'll also look for the function in the types namespace. So I've just gave you the general briefing, but this is the terms specifically. So template argument deduction, function template with the same name creates additional candidates for our list. And argument dependent lookup, searching on not only for in the function called namespace, but also in the arguments namespace, which is very important for our talk. We're going to use that quite extensively. And namespaces are ordered. That means that the inner one is the one to be searched first, and arguments are not ordered, and we can get ambiguity, etc. Now, additional thing that I want to point out throughout the talk, you're going to see those little squares over here. So I will later send the slides, and there's small code snippets demonstrating some of the things that are presented. And it's, I think, the best way to explore that is just to experience with those code snippets. So you're most welcome later to also do that. So to summarize, to compile a function call, the compiler must first perform name lookup, as we've mentioned, which may involve argument-dependent lookup, and for function templates may be followed by template argument deduction. If these produce more than one candidate function, then overload resolution is performed to select the function that will be called. If it's ambiguous, then compilation may fail, and we also have some techniques to avoid compilation fail, but that's not something we're going to go to in this talk. So I'm going to pause for a second, and if there's any questions, I'll be happy to answer them. This is a relatively, I think, complex and very interesting topic. Okay, let's move on. So now during the talk, we're mostly going to do an overview of the customization point methods exist in the library, in the library and the language in C++. And C++ was born with some customization point methods. Some of them, by the way, you already know for sure. More were added over the years. So we also have some more advanced things from C++ 23 and C++ 26. So let's show which customization points exist. So inheritance, as you've seen in the as I've mentioned, is one of them. Also, class template specialization. Original customization points that I mentioned by Eric that was suggested in the that was defined in the paper. That actually means ADL. Customization point objects, which is a new method proposed by Eric, and newer relatively. Concepts from C++ 20. Deducing this from C++ 23. Tag invoke that was suggested for C++ 23 but didn't get into the standard, and customizable functions that is not in the standard yet but being debated for C++ 26. In addition, some people suggest that reflection can be used for customization points, as I've mentioned. Reflection is in a very early stage, but we're still gonna briefly see what you have to offer. So as you can see, that's a long list, and I will go over all of those methods, but I might skip through some of the details. So again, feel free to explore the code snippets later and experience with them and see how this works in real life code. So let's start. So inheritance is something that I'm sure most of you are already familiar with, and people learn that once they even get into C++. but I don't think a lot of people at first look at it as customization points, and that's why I brought it. I present it here as a method. So let's see how that works. We have a library side, and we have library type, and it implements some functionality. It can either be mandatory that suggests that the user will mandatorily override that, or it can be optional if user is interested. And then we can also define some data and some terminology we can use using to define some name that we want to share with the user. So we're saying from now on, my int is int, and once user can also use that. And of course, also we can define some consts or other things as well. I would call all of those things as I mentioned, terminology and data. During the talk, we'll focus on functionality, but it's still interesting to see that this method allows us all of those. So library defines this lib type. As I mentioned, it defines functionality, data, and terminology. It can either define a mandatory interface by pure virtual functions or an optional interface by virtual functions. And then the library, knowing that this is the defined terminology, can also define this algorithm that uses such a type. So basically, the library can define libalgo, and this algorithm can assume that the type have func2, for example, and that it can call it. Now, the user, to be able to be conformant with that library algorithm, needs to promise that it does whatever the library type defines. And the way to do that is by inheriting from lib type, for example. So once inheriting, user gets all the terminology and data, but also the functionality. And now user can pass this user type to libalgo and get the expected behavior. So characteristics of this method. We're able to share interface, functionality, data, and terminology as a group. If we want to add additional function here and say that this interface is also needs func3, we can do it quite easily in the same group of functionality by just adding it here. And you'll see later that this is not the case for most of our customization points methods, the other methods. It's easy to opt in, and we can't accidentally opt in. As you can see, if we write a proper code, the user explicitly says that they want to override the functionality. It creates limits on the return type and runtime, and also have runtime overhead. We can use some complex methods to bypass that, but that's not trivial. And it's non-intrusive into library namespace. So library just defines something. We don't need the user to add things into the library side, which is also a benefit. But it is intrusive into the type. The type have to be changed in order to be conformant with this interface. And notice that there's this term intrusive containers in Boost. So this is not related to that. The term intrusive here is not related. So I just don't want you to get confused by that. And examples for customization using inheritance are everywhere. So every time we are doing something like that in our code, even without the addition of libalgo, we're customizing using inheritance. Any questions so far? Okay, great. So if there's any questions, just bring them up and I'll stop and answer. So we've now reached our second customization point method, which is called class template specialization. So as the name suggests, this is a template and we specialize it in order to get the customization point. So again, with the library and user divided areas, we have our library side, and library defines a template class called libtype with some deleted constructor, for example, in order to prevent a default creation. And now, library defines libalgo, and making it work specifically for libtype is not trivial. So we're going to see a bit later that concepts can help us limit that. But in general, it's hard for us to say which types can get into libalgo in this method, unlike the previous method was more restrictive. On the user side, user overrides the entire implementation. So we have here just template specialization. We specialize the lib type. So we have lib type and we specialize it for user type and override the implementation by saying, for example, in this example, what the constructor is doing. But it could be any other function as well. And user can instantiate and use this lib type. So we now instantiate this specialization type, and we can give it to the libalgo to be confirmed to whatever libalgo is expecting. But notice that we can pass, because we have to override the whole thing, we can't pass, as before, terminology and other things as well. So each of those things have to be separated. So there's additional things that we can do. We can also prevent, have some default used by the library or prevent this default. So as I mentioned, we don't have to completely delete the whole functionality. We can have some of the implementation by template specialization. But this is quite more complex. And one more thing that I want to mention is that I'm not going into namespaces here. In general, in the talk, the things under library are on library namespace and things on the right are on user namespace. But on this specific method, we have to get into the library namespace to change things, and that's also a downside. But as I mentioned, we can have explicit specialization on the constructor, and then we can have some of the functionality overridden. So we don't erase everything, we just erase functionality for full, erase in quotes. And we still can get other things. So again, user can instantiate this lib type and get the appropriate behavior, but we don't have to erase everything, which is great. So now we're going to see an example for class template specialization, but for functor. So before that, we saw that for types. So we defined some type and then use this behavior very similarly to what we saw in inheritance. But we can also do that for functor to define functionality. Basically, we're now focusing on the functions that we're customizing. So again, library can define this empty default, and it can implement function template. For example, here, library implements operator parentheses. And in this case, again, we can have a default. And on the second slide, I'm going to show that we can also have some delegation. So we can either have some default, just like in the previous example, we can have some default, or we can have no default, and we have to implement in the user side, but we also have delegation. So here, as I mentioned, we have only delegation in this slide. Next slide will be with some default. And basically, the libfunc is calling operator parentheses. On the user side, user override the implementation by template specialization, as shown here. It can also be done by inheritance. There are some upsides for that. And we get the proper functionality. We create this lib user functor. Okay, so this is basically a class that have operator parentheses and is behaving like a function, we can call it. And then this class that we've instantiated can be called with the user type and behave according to what we want. So this code will be called the user side of operator parentheses. All right. To specialize such a libfunc, the specialized libfunc that we just saw can now get the user type and use it. So as I mentioned in the previous slide, I've shown something that have no default, it only delegates. Here we can see something that have some default and then it delegates. So again, library defines this thing, and then default implementation also delegates call to the user. So we get both the library behavior and then the user behavior, which is a bit of a different thing in customization points terms. And user can overwrite again this functionality, but then we'll be able to see both of those behaviors. So we are now able to create this libfunc functor without customizing it here, and then we can call it. This is just the default func here from the library, the first one. And the second one is the one that we customized for the user type. So now both of those behaviors are available to us in the user side. Okay, so let's summarize this method. And I'm sure it's not a simple piece of code to go over very briefly, and we do have some limited time, but I really recommend you to go and look at those code snippets and play with this. So basically we have this method have to be a namespace or type intrusive. We have to add things to lib namespace. Different implementation can be provided, as we saw in the second example, like here. And if default exists, the indication is weaker. So like we wouldn't get anything from the compiler that says that we need to implement this default, because it's not going to fail, like in the inheritance. The compiler will yell at you if you don't implement pure virtual functions. But here we can't see that. And there's no mechanism to verifying the expected behavior. So basically, there's very little way for this libfunc to determine which types can be passed. But we can see it later that we have some way of controlling that. So example of libraries that are using such a mechanism is Fmt Lib. And I don't know if you heard, but Fmt Lib is the source for std.lib format, the standard library format library. And before that, there was an open source library written by Victor mostly, and others as well, called Fmt. And the standard library format is based on Fmt Lib, which uses this kind of mechanism. So everything is open source. And again, you're most welcome to search it and see it. So is there any questions so far? Feel free to ask.
Do you expect me to read them out to you, or would you read the Q&A section yourself?
I don't think I have an access to the Q&A, so I would love it if you can read it. Thank
Sure.
you.
So Shashank asks, how does constructor come from struct? I thought constructor was only for classes.
Oh, okay. This is yeah, I've sort of jumped over that. So in C++, struct and class are basically the same. The difference is that struct, if you have a struct, then the default access modifiers for all the members is public. So basically, struct is completely equivalent to writing class and public at the beginning of the class, and you get the same behavior. So it's confusing. I just wanted to save some space on the slides, but it probably wasn't the best choice. So sorry about that. I can't hear you, Hamil. Sorry, I think you muted.
Yeah,
Oh,
sorry for that.
no problem.
Abhishek Tanwar asks, do we use namespace to control the calls to user and library function?
Yeah, so on those methods we saw so far, the namespace is not completely, doesn't have a role other than the fact that we need to customize, the user have to add things to the library namespace. But in this methods that I'm gonna see just now, the ADL, yes, the namespace have more advanced role. And in general, ADL looks at namespace quite broadly. So we're gonna see it just next. By the way, that's not necessarily an upside. I think it's some people would suggest it's a downside. This is a complex mechanism, and yeah. Any other questions?
Okay, we'll take one more question before proceeding.
Yeah.
So we are not out of schedule. So Selva Kumar Jawahar asks, does smart pointer customization also fall under this class of class template specialization?
Yeah. Okay. So yeah, that's an interesting question. I wouldn't address smart pointer as customization point because it's more of a utility. I would more address it as a utility because in a way it's true that you can pass it to the library, back to the standard library algorithms and so on, but it's not necessarily something that the library exposes in order for the user to customize that is related to the algorithm. So a better example would be swap. If user code implements swap, then that's something that is being ported back to the algorithm. The algorithm asks the user, how do I swap your type? So this is like a better example. But I mean, it's really depends on the situation and the code exactly, but I wouldn't call short pointer in this context customization point. But it's true, it uses the same technical mechanism of template specialization. That is true.
Yes.
Okay, so let me move on to our next methods. And yeah, and you can see this is a very rich world, the world of customization in C++. So now we're going to go into what is called the original customization point, the thing that was present, that was the terminology that was mentioned in Eric's paper, but this is the mechanism that was exist before Eric's paper, that was the mechanism used to customize the standard library, and it still exists until today. As I mentioned, some of the things that currently exist in algorithms use this mechanism still. So what does it mean to use ADL? So I just want to mention again, what is ADL? ADL is argument dependent lookup. So this means that we're relying on the fact that the compiler not only searches for function names in the current namespace that we're at, also goes and search for functions in the namespace of the defined types. So again, if I have a foo that takes user type, the foo would be also be searched in the user namespace, and not only in the current namespace. Okay, so very basic thing that I want to show here, and this will open the discussion on ADL, is that basically the compiler is searching for the best candidate. Always, this is something that happens even in everyday code. For example, if we have a const type and just a type, then we can define different versions of the same function, and the correct method would be called according to the constants of the type. So this also allows us porting behavior from the user. So this is the most basic thing that we can do. So overload resolution, as I mentioned, can be affected by ADL. So if we have those two lib funcs, it's not only going to be searched for libfunc as in this namespace. We can also expect that the compiler will search for this in the user space. And as I also mentioned, template specialization is also something that is being considered for the overloads, but also from library space or non-template functions in user space if they have the same name, or non-template functions in user space using friends, which I'll mention soon. And as you can see, this behavior is not very simple. So the main problem with overload resolution as a mechanism for customization points is that there are a lot of different mechanisms that are all affecting the overload resolution, which candidate the compiler will pick. And these are all can sometimes collide and and create something that is very complex and unexpected. So let's look at a real life story, swap. I already mentioned swap before. Swap have been with us for a very long time. So you can see people are asking, and I'll give the again the general what we're trying to do here. So I have a user type, for example, and I want to give it to the library algorithm, to the standard library algorithms, and I want to say how the swap is being done in my type. So for example, if I have a very heavy type, but it only have pointers, and I also keep this, I don't know, additional int, I want to say that the swap is only involved in swapping the pointers and maybe swapping the values. So I want to, and maybe do something else that is specific to my type. So I want to tell the library, basically in this case, the standard library that writes an algorithm, what's the best way to swap my type, which will be probably cheaper and most effective, and also very importantly, it have to be correct. So someone asked in Stacks Overflow how to overload swap, and that's a reasonable question. And then they get an answer. The right way to overload std swap is by using argument dependent lookup, by defining in this class, this is the user class in this example, the class X, and they define their own swap as a friend function. So this is friend void func swap of how to swap my user types. And the answer in Stack Overflow is this is the best way to do it. This mechanism using argument dependent lookup. So then someone else answers, I'm sorry, the same person says that it's unspecified in 03, and some other people say that still using ADL is they would be surprised if the library is still using ADL. As I mentioned, this is an old mechanism, but still used. And somebody should check how MSVC implements that. And someone else says, yeah, I don't think that's a good idea doing that. I think it's not going to behave properly in the compiler. And then someone suggests that GCC is not standard conformant, so it doesn't conform to the standard, which I think is probably not true. And there's quite a lot of more of discussion, and I just want to mention that person A and person B that I've shown are esteemed members of the ISO Foundation, and there's, as you can see, quite a lot of discussion going on throughout the years. Sorry, and the last person that I wanted to show you have asked this question on this February, and it was right before I've prepared my talk, and then I went back to Stack Overflow and seen if there's any updates, and then I found this question from this person not long ago asking, what's the purpose of friend there? So that's a reasonable question, and we're going to answer on that in the next slides. But again, I just want to mention that, as you can see, ADL is a complex mechanism and still being asked, and questions are coming up about it. So let's see, how do we use this friend, and what the best way to overload swap. So as I mentioned, we're using ADL in this mechanism. And we defined this libfunc functor. And then this is the libfunc generic call. And libalgo also, sorry, this is a type. And libalgo also takes this type and expect, as we previously mentioned, some behavior. So this utility can be used by libalgo, but the user have to override implementation to be discovered by ADL, by free function or friend function. So basically, in the example below, the user could define swap in their own namespace as a free function. So they could define a void swap user type A, user type B, or a reference, of course, or they could define it by friend. And defining it, here you can see the example, defining it by friend actually means that this function here, the void libfunc, etc., is being exposed to the external namespace. So the user namespace right above user type can see this libfunc function defined inside of user type. Okay, so this is completely equivalent to a free function defined in the user namespace, but it has some advantages in the compiler aspect. So again, the friend can be seen by the enclosing namespace, in this case, user namespace. And the advantages are that while the compiler is doing this complex search for the proper function as part of the overload resolution, it have fewer candidates, because if we would have defined that in user namespace and we defined other functions, free functions called libfunc for other types, for example, like we can do with swap, then the compiler will have to go throughout the whole namespace and search for the proper things, etc. But if we limit this only with friend only to this class, then the compiler knows to only search that in the second phase, ADL phase, and it have fewer candidates. That means that the compilation will be faster. So that actually makes life easier for the compiler. So again, this is a term that is quite interesting. It's called hidden friends. The fact that we defined a friend here and it's been seen by the external namespace. And you're again welcome to go in search of uses of this interesting mechanism. So to summarize, we can basically call libalgo with this user type, and the compiler will see this libalgo defined in lib namespace, but also see this libfunc. The libalgo will also see this libfunc defined for the user type. This is exactly what happens with swap with the standard library algorithms. We get this algorithm, for example, sort, and sort know how to go and search for your own user's defined swap function. Okay. So to summarize this method, porting functionality for user type is possible. So as I mentioned, we have this libalgo, and it can use the libfunc defined by the user. This is non-intrusive into lib space. It's intrusive into user type. That means that we need to change user type to get this specific behavior, but that's reasonable. Trusting overload resolution is complex. As you've seen, a lot of things are affecting overload resolution. This mechanism of the compiler to find the appropriate candidate of the function is complex, and that's one of the reasons there's a lot of bugs in this area, and this is a complex method. The mechanism is based on names, so we have to reserve names globally. And as I mentioned, things like operator stream and swap and begin and end are all been using this mechanism. Okay, so as I mentioned, the paper before by Eric, there was suggested a new mechanism to be used And Eric have mentioned some of the problems that I've mentioned before, and also something that is a bit more complex, that we have to manipulate ADL in order to bring those into our namespace. But I'm not going to go deep into those problems because I want to move on to our next methods. So again, feel free to overview them later. So Eric have mentioned something that is called customization point object. So customization point object is trying to do something very similar to what ADL is doing for function names, but it is also trying to limit the call to some functor object, just like we saw before. And when we get to that object, then we start manipulating the names and decide which function we call. So I'll go very briefly over that. Library side defines this link func, creates libfunc functor with template operator, and creates global libfunc functor. So this is something that needs to be global in order for us to be able to call it. So this is basically a functor, a class with an operator parentheses, but we define an instance of that in the global namespace. And then once we call this object, it's been recognized. And user can also create this in lib functor to accept user type. So this allows us to port functionality for user type into libspace. It's non-intrusive because we only, in order to customize that, we basically create this instance and fill this with logic. It's based on names as before, and it's complex. We can't have, the main issue is we can't have this object in the global namespace because it might clash with function names. So we need to do some very special tricks and magic to be able to have this functor in the global namespace and not clash with other functions. But it's very broadly used in the ranges library, and it solved a lot of problems and issues that we have with ADL. So if you're now, instead of using stud swap, use ranges swap, stud ranges swap, you'll get this mechanism called behind the scene. And as I mentioned, it's basically considered inferior. So for the next few customization points, I'm going to go quite briefly over them because I'm not going to go into the details of the mechanism as much as I did here, because some of them are relatively new and some of them are not even existing in the language. But I still want you to get the general idea of how so many different ways that we can do those things. So very briefly on concept. Concepts, as I hope a lot of you are familiar with, is a way to limit our template deduction. So basically, this is something that in this context is used to control ADL. So we can control which functions will be called and which types will fit any functions. As I've mentioned in the previous slides, we have some way to do that. We have some way to customize that, and concepts are the way that we can address that. So concepts create clear code. It's not same as ADL. It might be namespace intrusive, and we need to reserve name globally. And we also have similar situations to the ones we have in ADL. We can still have concepts that are crashing with one another. If we have, for example, in type, we can clash with flow type or something along those lines. And they're also a bit limited. So there's a way to extend that beyond the limitations of concepts, which are only care about names that semantically constraining, but I'm not going to talk about that in this talk. Sorry, syntactic constraining. And ranges library is using concepts quite heavily. So deducing this is our next method. It's been added to C++ 23. and relatively new mechanism. It was proposed by Gasper Iman, Cy Brand, Ben Dean, and Barry Reflin. So thank you for them. It allows specifying the value category of the expression from within a member function. So in this example, these are just functions that are being overloaded for different value categories of the object. And here we can explicitly specify by using the this keyword the type of the parameter. So basically, we were able to pass this parameter explicitly, unlike here when we have it implicitly. Okay, so this allows us to have some template to define all those different things. And it's basically porting the usability at compile time. So to summarize deducing this mechanism, we can basically use deducing this in order to get something that is similar to CRTP. CRTP is also a quite broad topic, but it's basically allowing overloading in compile time. It's a mechanism that is very similar to virtual inheritance and generally inheritance, only done in compile time. And of course, it's limited to static dispatch and not dynamic dispatch, but it's been used where we want to save runtime and we care about those things. We get those in compile time. So deducing this basically allows us to have a better CRTP behavior, and that's also extends our abilities. So as I mentioned, this is very similar to inheritance, but in compile time. So we can basically customize the functions and get the proper behavior. And it's not intrusive, it's expressive, at least relative to CRTP. If you've ever need that method, you'll see it's very complex. So this one is a bit clearer and more expressive. And there's no need to reserve them globally. So basically, it's a very, very useful mechanism for a lot of things. And I expect that in C++23, we're going to see some customizations in libraries depend on this deducing this mechanism. So tag invoke was suggested for C++23, but eventually didn't get into the library. It was again suggested by Louis Becker, Eric Nibler, and Kirk Schupp. And one of the reasons this didn't get into the library is that we have some better mechanism that tries to do something very similar to what tag invoke is doing in the library, but on the language side. And we're going to see it in the next slide. But as I mentioned, this mechanism is complex. And again, I'm not going to go over all the details because this is a long dispatch mechanism. But you can see this in a very nice implementation called duck invoke. It's an implementation by René Fernandez Rivera Moral. And this is basically the simplest implementation I could find for tag invoke that can be easily played with and works great. So basically, the general idea is that library defined this libtag object. And library-defined libfunc delegates to libtag. And again, there's macro, and not all of this code fits the slide, but basically the macro defines two things. It defines a static struct and a reference. And on the user side, user-defined functionality using this reserved word. And we get the expected behavior. So to summarize, when we call, user can define tag invoke libspace for user func1 or for using func2. Okay, so these are two different implementations. And when we call this libfunc with user func1 as the first param, this has been triggered back to the library doing this delegation to the libtag, etc. Again, complex mechanism. And we go back to the proper to the expected implementation that we wanted to call. And if we do the same thing with the user func as the first object here, the different user func, the user func2, will get this function called. So basically, library is doing very complex things on their side, but user only needs to overload those functions in order to get the proper behavior as expected. And we can also do, as similar to sorry, to the previous methods, we can also do some delegation that also calls library implementation and so on. So it has some ways to customize. So tag invoke solves almost all of the previous problems that we saw, but it's a complex mechanism, and the communication with the user is limited. Diagnostic is complicated, and it also have very bad. I mean, performance are not great because the compiler performance of this whole dispatch mechanism can be quite problematic. So there are some libraries using this mechanism. But as I mentioned, we don't get a tag invoke into the library because we have something that is trying to do something very similar, but in the language. And this one is being considered for C++26. So customizable function is basically trying to do those complex dispatch mechanism the tag invoke is doing in the library, but only doing that in the language. So this is the syntax that was proposed when I wrote this talk. By today, I think the syntax have been changed. So the virtual, etc. This is just the syntax that was proposed in the paper back then. So again, this paper is still in progress, and don't address this syntax as a final one, but the general idea is the same. So we're basically trying to do something very similar to what being done in inheritance by marking things as virtual, meaning that we want to overload them, and by marking them as pure virtual, meaning that we want the user have to overload them. And we're doing those things only to templates. So it's very similar to what we know from virtual functions, but it doesn't use dynamic dispatch. This is not a virtual as you know it from C++ right now. This is just saying that this function needs to get some implementation from the user side. So again, user can add implementation in user space. No need to reserve names globally. We can easily opt in. It's again very similar in the concept to inheritance. We know that we need to override this functionality in the user side. Only it's been done, the dispatch has been done statically. And examples are for not exist yet, but future imagine execution. So I will finish the last slide, and then I'll go into the questions. So reflection, again, as the previous customizable functions method that I mentioned, is not finalized yet as well. Reflection is being planned for C++26, but some people suggest that we can do some of those customizations by using reflection. So basically, the library type can break the user type into different components and reassemble them and get the behavior that it wants. So to the most basic thing that it can do is basically, if the library implements some algorithm, it can break the user and get the swap from the user or whatever by using reflection. But again, reflection is not finalized. It's only been planned for 26, and we still don't know if we'll be able to use it as the ultimate customization. So to summarize, there's different ways to compare customization points. I'm not going to go over all of the details here, but there's this table that you can later go over, and these are the way that I see the different customization points and comparing them one to another. Can we share functionality between the user and the library? Can we share data, terminology? Can we opt in explicitly? Can we explicitly say, I want to override this function? Or do we need to change our type in order to get that? Is this type intrusive, etc.? So again, a lot of different ways, and we'll see what's coming next in the next few years. So as I mentioned, execution that wanted to use tag invoke didn't make it to C++23. Possible changes in customization points might have been the reason. Tag invoke was basically right now neglected, but language customizable functions is the thing that is trying to replace it, but using the language mechanism. And maybe reflection can solve those problems, but we don't know how reflection is going to look like because it's still being debated for 26. So I would hope that we'll be able to solve all of those for 26 and get this new mechanism that I think is relatively promised to do some customizations between our library and user codes. And meanwhile, we're going to have to settle with those existing non-language solutions. So I would love your inputs on this, and thank you very much for listening. Okay, so we don't have much time for, I'm just gonna show my thank you slide. We don't have much time for questions. So I hope you enjoyed, and I know it's been quite extensive. This talk was originally planned for an hour and a half, but I did want to taste the different mechanisms and the variety of complex mechanisms exist in the language and in the library. And this topic, bottom line that is most important to me to say is that this topic is still in progress. And I think you still can affect how the customization points will look in C++. So I will welcome all of you to go into this topic and suggest changes. And maybe your customization methods will be the one next to be used in C++.